You want to take Good morning, everybody. Want to welcome everybody to the sixth week of the Rugby Research and Injury Prevention Group 2025 Analytics Series. Before we start, I would like to take a quick little picture. So if everybody gets on the camera and look at the camera, I'll take the picture in three, two, one. All right, there you guys. Actually, let me take one more. Sorry about that. Um,
Yeah, if you're able to, please turn on your camera.
okay, I'll do it once we all join in. Okay. All right, so I'll take a picture in three, two, one. Thank you. Okay, so like I said before, welcome to the sixth week of the Rugby Research and Injury Prevention Group 2025 Analytics Series. I want to begin by introducing our first intern, who is Lawrence Cangro from the Alabama College of Osteopathic Medicine. Lawrence is going to be presenting today on logistic regression overview. So Lawrence, whenever you're ready, could you please share your screen?
I think I just sent over a request to share my screen. There we go. All right, so I'll be presenting on logistic regressions. So first, I'll start by talking about what is logistic regression. So it's a method to model relationships between different variables. It allows us to infer, predict a variable based on one or more other variables. And specifically for logistic regressions, this will help you predict categories like yes or no, those two-sided variables. So like if somebody has a disease or if they don't have a disease. So logistic versus linear. In a linear regression, you're going to see values that go past 1 and that go before 0. And this doesn't make any sense for probabilities. So we need something that always stays between 0 and 1. And that's one of the reasons we use logistic over linear regressions. So how does logistic regressions make predictions? So it creates a score using this formula you see below. So score equals weight times input plus bias. Your input is going to be your data. So someone's income, their age, test score. And then the weight and bias are going to be something calculated by a computer. The weight is going to be how important an input is, and the bias is going to be a constant that will adjust the score up and down. And once you get that score, you can convert it to a probability. And then if the probability is greater than 0.5, that's going to be a yes. And if it's less than 0.5, that's going to be a no. So using that score we just talked about, this is how we get our probability here. You see this equation over here on the right. So this is a sigmoid curve here. And the formula is going to turn anything between, going to turn that score we just talked about into any number between 0 and 1. And this is going to let us calculate that probability we're looking for that yes or no answer. So you have to train the model. So the computer is going to try a bunch of different weights and biases based on your data. It's going to choose the one that makes the most predictions that match the real data. And this overall method or training the model is called maximum likelihood estimation. So we're going to go into an example. So we're going to try and predict whether someone will buy a luxury car based on their income. So we see this data here, person A through J, and just increasing incomes over here. 0 means they're not buying a car. 1 means they are. So we see around 50,000 income. That's they're gonna start buying cars. So looking at how we can predict that, the data is going to be entered into computer, and it's going to process this data and make predictions based on the real answers in the data. So the income and who buys the cars. It's going to adjust the weight and biases, and then it's going to repeat this process as many times until the predictions are as accurate as possible. So we'll say the model learned that it has this specific weight of 0.0002 and a -10 bias. It's going to calculate a score, and then it's going to plug that score into the sigmoid function. We see here it pops out a 0.88, which is going to be an 88% chance that somebody with a say $60,000 income will buy a car. So in overall summary, logistic regression will predict binary outcomes, uses a sigmoid function to produce probabilities. It's going to make decisions based on a threshold like 0.5, over that being yes, under that being no. And then it's trained by finding the best weights for the data. And here are my references. If anybody has any questions, please let me know.
All right, Lawrence, thank you for that excellent presentation. Like Lawrence said, if there's any questions, or let me see if Dr. Lopez, oh, he's not here. But if you guys have anything to add, please feel free to add. If not, I'll move on to our second intern. Our second intern is Nadira Peaks from Adelphi University, and she's going to be presenting on linear regression overview. Nadira, whenever you can, please share your screen.
Thank you. Can everyone see my screen well?
Yeah.
Thank you. Okay, so as Gabriel said, my name is Nadira Peaks, and today I will be presenting a presentation on understanding linear regression. So to start off, what is linear regression? Amazon Web Services defines linear regression as a statistical method that predicts the value of unknown data by using another related and known data value. It essentially mathematically models the unknown or dependent variable and the known or independent variable as a linear equation. The goal of linear regression is to establish if there is a relationship between the two variables. So an example of linear regression could be a study used to investigate the relationship between weekly training load and injury risk for professional rugby players. The weekly training load could be referred to as the independent variable, and the injury risk for professional rugby players can be referred to as the dependent variable. In this plot to your right, there is an example of a linear regression model plot, and I will get into the specificities of each of the plot in a future slide. So why should we use linear regression? Well, mostly because it helps understand relationships between variables, it helps predict outcomes, and it quantifies the strength of associations. Linear regression has a lot of applications, and it's most widely used in economics for predicting income, health sciences for predicting blood pressure, and business for predicting forecasting and business goals. So here we have the actual mathematical model for linear regression. It says y is equal to beta naught plus beta 1 times x, and it's added by epsilon. So what do these variables mean? Y stands for the dependent variable, x stands for the independent variable, beta naught stands for the intercept, beta 1 stands for the slope, and epsilon means the error term. Epsilon is the difference between the actual versus the observed values, and it calculates variability in a dependent variable. Beta naught is the intercept, which I have made a circle over here to indicate the regression line, the line of the slope, passing the y-axis. It's essentially when y is what the x value is when y is equal to 0. And yes, the beta 1 is the slope, which is over here. The slope shows how much y changes for 1 unit increase in x. So there are different kinds of linear regression, and two common types of linear regression are simple linear regression and multiple linear regression. The only difference between the two types of regressions is the number of independent variables that they use in their regression. So in the left over here, we have an example of simple linear regression, and it uses study time as an independent variable. And to your right, we have multiple linear regression, and it uses study time and IQ score for independent variables. So it's essentially a difference in the amount of variables that are used for each type of regression. So there are a few assumptions that need to be cleared before we can get into the linear regression. Regarding linearity, there must be a linear relationship between independent and dependent variables. It cannot be nonlinear. Regarding homoscedasticity, the error term must have constant variance. And regarding normality, the error term points must have a standard normal distribution. If data points were to be plotted, the histogram would need to have a standard normal distribution or standard normal curve. Regarding multicollinearity, there cannot be high correlation between the independent variables, but this only refers to when you perform a multiple linear regression. And with autocorrelation, the error terms have to be independent of each other. They cannot be dependent of each other. When fitting data into a linear regression model, there needs to be the best fitting line that represents the relationship between your data points. And the best fitting line is usually found using the least squares method. The least squares method attempts to fit a linear regression trend line or slope as closely as possible. So in the picture that we have over here to your right, you can see a least squares regression, linear regression. The blue data points represent error terms, and the slope represents the line that is as closely to the center of the error terms as possible. So there are a few things to consider when interpreting linear regression output. The intercept, or beta naught, is, as we know, is the predicted dependent variable value when the independent variable value is 0. The slope, or beta 1, is the change in dependent variable for each 1 unit increase in the independent variable. When looking at the coefficient of determination, or aka r squared needs to be in between 0 and 1. And the coefficient of determination essentially quantifies the proportion of variance in the dependent variable that is explained by the independent variable or variables in the model. So a higher r squared or coefficient of determination means a better fit for the linear regression model. However, it is important to note that it does not signify a statistically significant relationship. Moving on to a p-value, we know that p-values help determine if there is a statistically significant relationship between a predictor variable and a response variable. A p-value that is less than 0.05 indicates that there is a statistically significant relationship between the predictor and response variables. A p-value that is greater than 0.05 indicates that there's not enough evidence to support a significant relationship. So understanding residuals. In order to understand linear regression, you must first understand residuals. What are residuals? Residuals are the difference between the actual dependent variable values and the predicted dependent variable values. Residuals essentially show prediction error and model fit quality. When plotting residuals, you need to make a residual versus a fitted plot. So to your right over here, you can see this is an example of a residual plot. The x-axis pertains to predicted dependent variable, and the y-axis would represent the residuals. These blue data points represent the error terms, and what we essentially want to look for is if they look randomly scattered or scattered around 0 in the the x-axis. Patterns that have, or data points that have patterns, or we can see there's a clear relation between the data points, suggest nonlinearity or unequal variance. In addition to understanding residuals, we must also understand QQ plots. So what is a QQ plot? A QQ plot stands for quantile-quantile plot, and it compares theoretical quantiles and sample quantiles. Essentially, QQ plots checks if residuals are approximately normal on the plot. When interpreting QQ plots, you want to make sure that the slope, it points in a 45-degree angle. and that indicates that residuals are normal. But if the slope is S or shape curved, or even slightly curved, it represents possible skewness or tails in the standard normal distribution. So why does this matter? QQ plots validate assumptions for p-values in confidence intervals, and they confirm if linear regression is a good model to use or not. So in sports epidemiology, linear regression is very useful. It quantifies relationships between exposures, for example, training load, surface, age, or BMI, and injury outcomes. It can also support evidence-based recommendations for training load management and injury prevention. It enables risk modeling for different athlete populations and contexts, and it provides interpretable coefficients to communicate findings clearly to coaches, athletes, and stakeholders. So some key takeaways that you'd want to learn from linear regression is that they model the linear relationship between two or more variables. And there must be assumptions that have to be checked for validity. A residual plot and a QQ plot are great tools for confirming the validity of a linear regression model. And as we go into our research questions, linear regression will become a practical use as we tackle complex statistical analysis. Here are some helpful resources that are posted on the internet that will help you in your journey to understanding linear regression. These are my references. Thank you. Are there any questions or comments?
Hey, Nadira, I thought that was a great presentation. What I'd like to add, and I think that was really great that you touched on residuals. Because a linear regression, it maps out the best the best fit for the line. The residuals in total add up to 0 because they have to be balanced apart from the line. So I think that's a really important thing to understand, especially when we talk about residuals, because it reinforces how the line of best fit really is in the middle of all of our data points.
Right, yes. Thank you.
Thank you, Nadir, and thank you, Philip, for your input as well. If anybody has any other input, any other questions, please feel free to ask. If not, we'll move on to our third intern, who is Philip Tiesick from the University of Michigan. Actually, Dr. Lopez, if you have
Yeah,
any.
just have one quick question point. I think Nadira, thank you for bringing up the R coefficient. I think due to the fact if you have the right amount of variables, and I think I don't know who's on the call, but the importance of that is if you have the right amount of variables, it supports the model, and the model therefore, and I think you clearly stated, doesn't give significance, but what it does do is it allows the model to be validated for the linear regression. And maybe we can expand on that a little bit so this way everyone's clear on that. Maybe Nadira.
Yes, so yes, while the coefficient of determination, it doesn't give statistical significance for a linear regression, it does do a good job of validating the linear regression model as a whole. So it also does not give causation, I believe, give any evidence to having good causation in the model.
Right. It doesn't have any, there's no causation or correlation,
Right.
but it does validate the data points within the model. So let's just break it down simply. All right. With our RRIPG reporting system, if everyone who has attended an event understands, those data points all build up to a certain thing. So if we want to do a correlation between tackling and head injuries, we can do that. So we can actually take part of our data, do that linear regression model, and then add that maybe to a video analysis in theory, because then this way it supports both analyses more so due to the fact that the data points you have within your model, but then also the, I guess, validation of the linear regression on how it looks on the plot line, and therefore supporting that. So it's almost like a a double support there. And then if you add another analysis to support this finding, it's that's why when you look at the analyses sections, there's multiple studies. There's chi-square, t-square. Then there's Bonferroni's on that to support that. So and then CI. So you have all these points building on each other to validate the overall model, the data points. So that's why when you see these tables, they're a little bit winded. As you saw with Dr. Roberts yesterday, he had quite a few points on that, right? On his let me rephrase it. He had the diluted version, but if you saw the paper that was sent out on the knee injuries, there was quite a few data points. That's the difference of what I was trying to say. It's a great job the way Dr. Roberts diluted the data so this way you can understand it. And that's what you try to do. You try to do that translation. But again, we're going a little bit off topic, but more importantly, like I said, the model's really the key. If you put together an appropriate model, then you can analyze it further. And when you put these models together, you have to kind of envision your hypothesis. That's why I'm making everyone do the research plans, because in this way, it supports that. Okay? Thank you. Good job.
Thank you.
All right, thank you, Dr. Lopez. Thank you, Nadira. Moving on to our third intern, it's going to be Philip Tiesick from the University of Michigan. Philip is going to be presenting on receiver operating characteristics, or ROC curves. So Philip, whenever you're ready, could you please share your screen?
Of course. Thank you for the introduction, Gabe. My name is Philip Tiesick, and today I'll be presenting on receiver operating characteristic curves, also known as ROC curves. Receiver operator characteristic curves are graphs used to evaluate the performance of binary classification systems, and those are models that are used to evaluate between, as actually Larry talked about in his presentation, when there's only two options of categorization. So either in the form of a yes or no, or competence in healthcare, diseased or well, or infected or uninfected, immune or unimmune. And the ROC curves are used to evaluate the relationships within specificity and sensitivity, which is actually a topic that we went over in a previous analytics, but I'd like to just refresh on it. So sensitivity is the ability of a test to correctly identify those who have a condition. So those are known as the true positive. So out of all the people who are actually positive, for example, for an infection or a disease, just how well can we calibrate our tests to pick up on that rate of positive infections? Whereas specificity is the ability of a test to correctly identify those who do not have the condition. And this, on the other hand, would be known as a true negative. And the ROC curves evaluate the relationship between the sensitivity, the true positive, and the specificity, the true negative. So when creating a binary classification system, we often end up with a histogram that can tend to be split up into two groups. In this graph particularly, it is known as a bimodal graph because we have two humps, which is where we get the bi from, as opposed to a unimodal curve, also known as a bell curve. In this diagnostic test, one that has continuous values, we have the two different humps, one of which we can see for group A, which we could, for the sake of example, list as people with the condition, and group B, we could list as people without the conditions, respectively, the positives and the negatives. Using a cutoff point, we could try to classify which group or which values correlate with each group. So I put in three different examples here. So moving all the way to the left, if we were to put a binary classification cutoff value at around a value of 40, we would only be able to from there say, okay, if the value is greater than 40, they would be known as group A, or if it is less than 40, they would be known as group B, for example. However, in this case, that would not be very useful because it just does not line up very well with the differences between the two groups. And we can also see that up here around value of about 80. However, if we were to use a cutoff point around the middle, one that splits up the two groups much better, we would really have a successful cutoff point in this scenario because we would effectively balance out sensitivity and specificity, calibrating our test to differentiate between, in this case, group A and group B. So ideally, the proper cutoff point in an ROC curve would maximize sensitivity and specificity. Now, when running binary tests, we are going to oftentimes get many different types of bimodal curves. Oftentimes, it can sometimes be unimodal if there is not that much of a differentiation between the two groups. Now, in these three examples here, we have the two groups that are very much separate and would be easy to differentiate between. One that is almost completely unimodal, in which the groups are very hard to differentiate between, and then one that is much more realistic, in which there is a lot more overlapping, but it is still a bit easier to tell which group is which based off of the continuous values along the x-axis. Now, using an ROC curve to test the sensitivity and specificity, a perfect test would evaluate the movement of cutoff points all around the curve and would demonstrate 100% sensitivity and 100% specificity, graphing an ROC curve that has an area under the curve of the maximum, which is a whole value of 1. This value is gotten as the cutoff point is moved along the x-axis, finding that as, for example, here, right here, we could say if the value is to the right of this cutoff point, then we could label them as all diseased. Well, here we would have a 100% true positive rate because we would label all the disease correctly. However, we would also have a 100% false positive rate in which we label all of the well cases incorrectly. And this would also occur all the way to the right with our cutoff value here. And that is how we would get ROC curve that is completely square and reaches the maximum value of 1. In reality, ROC curves can sometimes overlap, and this would, in this case, perform no better than random guessing, in which at no point where we would move the cutoff point along the curve would we really be able to differentiate a point in which we could evaluate the binary classification system properly. In this case, the well and the diseased are completely overlapped, so at no point in which we would move the cutoff point along the continuous x-axis would we be able to balance out sensitivity and specificity, giving us an area under the curve of 0.5, which performs no better than random guessing because there's an equal rate of true and false positive rates. In a realistic test, as I mentioned before, oftentimes the two binary classifications can partially overlap, and this is what we see a lot more in real world data, in which there is a bit more of a balance between sensitivity and specificity. However, it is not 100% for both. And this can lead to an area under the curve that is in between 0.5 but less than 1. Now, evaluating the area under the curve, we are able to interpret just how well our ROC curve is functioning. So here is a general table that is used to evaluate just how well your test is working, all the way from a worthless test in which you only have an area under the curve of 0.5, which performs no better than random guessing, all the way up to an area under the curve of 1, in which we have a perfect test that balances 100% sensitivity and 100% specificity. Right here, as I mentioned before, with two groups that are completely distinguished, as we move the cutoff point along the line, we would always have either 100% sensitivity or specificity. That would give us an area under the curve of 1. Right here in our table, we would able to be labeling that as a perfect test with our interpretation because the groups are completely different in their classification. A perfectly bad test, however, if we were to move along the line, the cutoff point along the x-axis would not provide us any real discernible data between the groups, giving us an area under the curve of 0.5, which would be rendered as worthless. In reality, however, a lot of curves end up somewhere in between 0.5 and 1, and in this case, in which the two binary groups are somewhat overlapped, we could end up with an area under the curve of 0.77, which would be categorized as a fair test according to this table's interpretation. Now, summarizing what we spoke about today, receiver operator curves just generally plot true positive rates against false positive rates, also known as the sensitivity plotting against the specificity. And the main goal is to evaluate binary classification performance across these thresholds. Perfect model will have an area under the curve all the way at 1, whereas a model that is not very useful and functions no better than random guessing because the groups are completely overlapped will lead to an area under the curve of just 0.5. Cutoff point selection matters, and this can tell us about the ideal threshold balancing sensitivity and specificity. Here are my references, and I am open to any questions.
Thank you for that presentation, Philip. Just a general thing, can you quickly go over why the area of the curve can't be less than 0.5?
Yeah, so as we can see right here, because the area under the curve right here in a graph that completely overlaps in this example, well and disease, but just generally a binary classification system. Because they are completely overlapped, it is hard to get an area under the curve that is 0.5. And this is also sort of indicative of the um, the probability in which I've seen many people compare area under the curve of 0.5 to a coin flip, in which a coin flip, of course, is 50-50. And in this case, we're just having a value of 0.5, which just does not really give us any discernibility between these two groups as opposed to one that functions 100% of the time because the groups are completely different in their classifications, whereas here they are completely overlapped. But yeah, I think it's a great question. It is important to understand that that they can range from 0.5 all the way to 1, whereas in most cases and in most real world data, we'll see a value in between those two classifications.
That makes sense. Thanks so much for the explanation and the amazing presentation that really just goes over in detail, like the different scenarios in which this could be applied.
All right, Philip, thank you again for your excellent presentation. If there aren't any more questions, or Dr. Lopez, if you have anything to add.
Sure. I just want to make sure. Great job, Philip, on that. I think the number where I know Philip was talking about the 0.5 and the 1, but I do think the 0.8 has validity. When I mean that, I'm just saying that I think it's fair. The way they categorize it, Philip, you could bring that table up. I think most studies will tolerate a 0.8. Below 0.8, it's fair, but a good test is a good test. I'll take that any day, particularly with the so say, for example, one of our columns of data are a little weaker than the others. You need to be able to find a tolerance of what you think. And I guess Philip maybe want to comment on that.
Yeah, I think that just looking at like the interpretation, sort of similar to how p-value can be distinguished in the literature as needing to be under 0.05 for a significant finding, and confidence intervals are typically 95% confidence intervals. An ROC curve generally above 0.8 is known as a good test and is representative of a good relationship and distinguishment between the binary classification system within high-level scientific studies.
Thank you. One more point, and that is I want everyone to understand, there are limitations with this particularly, and that is, the ROC curves are overly optimistic. They can be overly optimistic on imbalanced data, and you have to be very careful on that. That's why I think they recommended, or be careful with imbalanced data sets. They can be misleading, imbalanced for examples of positive examples. Okay, so make sure everyone understands that. It's just that there's a limitation. It may look good and you may be above 0.7, like we were just saying, but you got to be very careful about that. Okay. Good job there, Philip.
All right, thank you everybody for your input, your questions, and your contribution to the call. Again, thank you, Philip, and all the answers today for your excellent presentations. That's going to conclude our call for today, and I want to thank everybody who joined us today on the Rugby Research and Injury Prevention Group Analytics Series. Thank you for joining us.